My name is Anthony Rizzo. Today I'm going to be giving my lab report over Lab 2 charge tapes. The purpose of this lab was to create a computational model of two charge tapes exerting an electric force on each other. We are going to then use this model to estimate the amount of charge on each tape necessary to float one above the other. Finally, we're going to compare the results of this to the results from Lab 1, where we were treating the tape as just having a point charge. So some of the fundamental principles we're going to need in this lab are using Newton's second law, force is equal to mass times acceleration to calculate the gravitational force on our tape, Coulomb's law, force is equal to Q times E to calculate the charge of our tape, and finally superposition, where we're going to be breaking the electric field into segments and adding together to find our overall E net. So a quick preview of the results. The net charge on one of the tapes is approximately 2.613 times 10 to the negative 8 coulombs. Force Fe should equal force gravity, which is approximately 2.06 times 10 to the negative 3 coulombs. And this model proved to be much more accurate than the point charge model at calculating the charge of the tape. So real quick, some assumptions that we're going to have to make for our results. We will again ignore air resistance. Each piece of the tape is assumed to have the same charge, and the charge on our piece of tape is assumed to be evenly distributed. So for our experiment, the system is going to consist of only tape B. The surroundings include tape A and also the tall objects, which we're going to suspend tape B from. Procedure is going to be identical to Lab 1. So we start by charging tape B by ripping off the base tape. We suspend it between these two objects. We introduce another charged piece of tape A. We raise that piece of tape A until tape B begins to float, and then we want to measure that distance between the two pieces. So for our experiment, the constants that we're going to need, G, gravity, and Coulomb constant K. The experimental data that we had to collect include the length of the tape, the mass of the tape, and the distance between the two tapes when tape B began to float. And our first calculation is going to be force gravity, which is equal to mass times acceleration, which are both known. And we're going to use this in our model to estimate the charge of the tape. On the right, you can see a snippet of my code where I'm just putting those physical constants in there and the observed values of the experimental data. So moving into the bulk of my computational model. So this is where we're going to start with the function to the function for the electric field. This is coming from what we did in Lab 1. Next, we are going to have another function that's going to create a line of charge. This function was included and we did not need to alter it. Next, we are creating the actual tape objects. So we are going to set up the top tape and bottom tape objects at the top of the screen. Next, we're going to be getting into calculating the actual electric field and electric force. So then at the bottom, we are initializing some of those variables. So finally, here we have our nested for loop, where we're iterating through each piece of the charge on the top tape. And then that's going to loop through. And then at the bottom, we have our arrows, which are going to help with our visualizations. And finally, just our print statements to print our findings for the electric field and force. So here's the final result. This one is going to be on the right under the new model, whereas the one on the left I wanted to show was the model that we created from Lab 1. So we can compare the data found there. So for the findings, this line charge model that we just made was much more accurate in determining the charge of the tape. Note, this model still isn't perfect because of the assumptions that we are making here. Some possible sources of error include the measurements of the tape's length, the distance between the two tapes when they begin to repel, and we are assuming the charge of each piece of tape is equal and evenly distributed. So some discussion questions. What if you had modeled each of your tapes as a single point charge, like in the previous lab, compare the estimated value you get? So the point charge model calculated the charge of a piece of tape to be 1.196 times 10 to the negative 8 coulombs, whereas this new model calculated it to be 2.613 times 10 to the negative 8 coulombs. So a very big difference here. Why do these estimates differ, and which is more likely to be closer to the real value? So we obviously are using different methods here. Lab 1 was we treat it as a point charge. This lab, we break it up into many segments, which is going to make this new model much more accurate, even though it is still not perfectly ideal. So in conclusion, using superposition to estimate the charge by splitting it up into sections is much more accurate than treating the object as just a point charge. And this model could be even more accurate by increasing the number of segments that we use in our calculation. Thank you.